Morning, everybody. I brought a balloon today because, balloons make everything better, right? So anyway, we'll get to the balloon in a second. We have a crown to manage. Before we get to the crown, tomorrow's quote-unquote lab, okay? Largely depends on how far I get today. I think I will get like 90% done chapter, whatever we're in, 14. And that'll be enough for you to do your homework. So I think tomorrow is going to be that open lab. There will be no lab activity. There will be no lecture. You can come, get help, get chapter 13 homework done, right? I will be there. I will answer your questions. I won't just smile at you, right? And I will be there from 8 until 2, right? So even if you're not, if you're not in the 8 a.m. and you want to come earlier or something, you could, right? And vice versa, right? So I'll just be there from 8 to 2 again. No formal activity, no assignment. You're not going to be docked for missing it. Wanted to give a little bit of extra time. Some of you have been telling me I've got like 3 or 4 exams this week and 10 next week, and then finals. There's all kinds of stuff going on. So a little bit of a pressure release valve here. Let's get chapter 13 homework done tomorrow, and then you can be focusing on 14 for the weekend because you have the exam next Thursday, right? Okay. So that's the plan for tomorrow. Any comments, questions, or concerns about that? Okay. I do hope to see you there, and I will be sad if you don't come, but I'll also understand. All right. The crown, right? Time to apply this Archimedes principle that we have been playing around with. Just as a very quick review, remember that the buoyant force, the force that causes things to feel this upward force in the presence of a fluid, is the result of the weight of the fluid that gets pushed out of the way, the displaced fluid. And we describe that weight with rho GV. Right? Density of the fluid, volume of fluid displaced. That's where you've got to be careful. You've got to make sure you understand which volume is being displaced. The examples I'm going to give today, it'll be the complete volume that's displaced. But if you're told like a boat is floating with half of the boat submerged, make sure you only use half of the volume of the boat, right? So, all right. So we have this crown, right? This unknown object. And something that's a little bit peculiar to chapter 14, to physics. When we talk about weighing something in air, physicists get a very specific picture in our head, believe it or not, okay? And this is perhaps a tad old-fashioned, but maybe you've seen one of these scales maybe like in the supermarket, okay? Where you take your grapes, your broccoli, whatever it is you're buying, right, and you put it in the basket, and then the little dial above tells you. There's another kind of scale that's got the platform, you put it on there, right, and the dial is down below, right? When we say something weighs a certain amount in air, and for a physicist, that means we've got like one of these hanging scales, right? And so the scale is reading the tension in that string that's attached to this mass that's hanging there, right? Okay. So what we're saying is, right, that gravity is pulling this down, the tension's pulling it up, and it's this reading, right, of that tension that the scale gives. So as long as the scale and the mass aren't accelerating, the scale is going to tell us the weight. But just so you kind of get a little bit maybe of the right picture in here, because when it says that this object is weighed in air, right, the picture a physicist would get in their mind is, well, it's hanging from a string. And then, right, so this is 300 newtons, right? And then it's put inside of this container with this liquid, and it's weighed again, right? Its mass didn't change. Where did its weight go? So the water got displaced, which gave rise to the buoyant force. And so the discrepancy between these two numbers, the 100 Newton difference here, is the buoyant force. And so if we draw a free body diagram, right, of it inside the liquid, I mean, gravity still pulls down on it. the same as gravity always does. Gravity doesn't change. It's this extra buoyant force that gets added, right? So while it's hanging in air, we've got the tension up and the weight down. And when it's inside the fluid, we now have two forces that are pointing upwards, the tension and the buoyant force. So in air, okay, I should stop drawing arrows. In air, right, we have T minus mg, but here when it's inside of the liquid, we have T plus the buoyant force minus the weight. That was a very sloppy beat. And so that's, so here, right, this is reading 300, and over here, this is reading 200, right? That tension changes as it goes in to the liquid. All right, so we know something, right? We know that the buoyant force is equal to 100 newtons, right? Because the weight had to go somewhere. We also know that that buoyant force has to be the density of the fluid that got displaced times little g times the volume of the fluid that got displaced. If we're going to find the density of this crown, this object, maybe it's not. Maybe it's a lead imposter. Looking like a crown. We need, well, they're telling us find the volume. And then once we have the volume of the object, how do we find its density? Which is really, that wasn't a really hard question. So is it too early in the morning still? Yes, mass divided by volume, right? Okay, so that's our goal. Let's see if we can get this. All right, do we know, so we know the buoyant force, do we know the density of the fluid that's been displaced? Yes and no. I haven't taught you about specific gravity. Specific gravity, I dropped it into this example because I wanted you to be aware. You'll see this on the internet a lot. You'll see it in chemistry textbooks, some physics textbooks. Physicists, we tend not to talk about specific gravity too much, but it's a thing. Specific gravity is the ratio of the density compared to water. So in this case, with a specific gravity equal to 0.7, okay? To find the density of this thing, you would take 0.7 and multiply that times the density of water. Now, for a physicist, again, that's 1,000 kilograms per cubic meter. Right? If you're in chemistry, you're operating in grams per cubic centimeter, but that unit's going to screw you up doing physics problems. So in this case, the density of our fluid is 700 kilograms per cubic meter. So whenever you're told the specific gravity of something, it's just multiply by 1,000, right? And you'll have the density of the object. So if specific gravity is 0.5, then what's the density? 500, right? If it's 1.2, then what's the density? 1,200, right? It's just like a kind of a really quick way to communicate, especially how things will float in water, right? Okay. So if you have a specific gravity at 0.9, you instantly know that 90% of that object is going to be below the water. Right? So that's kind of how that rolls. All right. So we know the density of the fluid displaced. We know which planet we're on, and we know the buoyant force. That means we can go ahead and solve for the volume of fluid that got displaced. That's going to be the buoyant force, 100 newtons, divided by our specific gravity, 700, times 9.8. When I did that, I got 1.46 times 10 to the minus 2 cubic meters. So there's our volume. That is the volume of the fluid that got pushed out of the way. But what else is it also the volume of? The object. And why is it why are those two volumes the same? Close. Something very particular you need to focus on to know that those two volumes are the same. It's fully immersed. It's completely surrounded in its liquid medium. If this were a boat, I know I just said this, but it bears repeating, right? If you've got a boat or an iceberg, or let's do a polar bear. Polar bear's green. Okay? If that polar bear, right, is sitting there, and 50% of that polar bear is below the water, and we solved for volume of fluid displaced, you would not then say that that is equal to the volume of the polar bear. You could say that's 50% of the volume of the polar bear. You see what's going on here? So make sure you know whether or not something is completely submerged or immersed in the fluid you're talking about. Is this balloon completely submerged in the fluid? Yes, it's completely surrounded by air, right? So again, just be aware of that. Okay, we got the volume, okay? Now we need to know the, okay, so to find the density, I need the mass. They didn't give me the mass. How do I find the mass? Ooh, we know the weight in air, don't we? And we know that weight, this 300, is equal to mg. So, no problem. Divide by 9.8 to get the mass. I did that. I got 30.6 kilograms. That's a, it's like a 60-something pound crown. I hope this isn't a crown. So there's the mass. And now to get the density, I take my 30.6 and I divide by my 1.46 times 10 to the minus 2 to get 2.1 times 10 to the 3 kilograms per cubic meter, or 2,100 kilograms per cubic meter, which, if I remember correct, is closer to lead than gold. Maybe. I forgot to look up the density. There you have it. That was essentially, definitely a more modern take with modern physics involved. It's essentially what Archimedes figured out, right? In that afternoon, sitting there at the bath, right? That aha moment, realizing that the buoyant force was equal to the weight of the fluid that got pushed out of the way. And then he was able to kind of backtrack and do some experiments to find out. History does not record what the crown was ever made of, or what Archimedes discovered. It was more importantly, he discovered the relationship and that he had a wardrobe malfunction, apparently, because that is definitely something that sticks. Oh, more not smiling people.
If we place this helium balloon inside a glass jar filled with air, it floats to the top. If we replace the air in the jar with helium, what will happen to the balloon?
All right, what do you think? What's the balloon going to do if we put helium in the jar instead of air?
Sink.
Sink? Why will it sink? There's helium in the balloon.
Because the outside and the inside is the same.
Okay.
The air itself is the same.
Okay, so the gas inside and the gas outside are the same, which means it shouldn't, like, it's just so,
doesn't change.
okay, the density doesn't change, but so why would it sink?
Because it's uniform.
Pressure differential? No. Again, you're not seeing something that's right in front of your nose. Ah, the balloon material itself, right, has mass. So right now, this is a helium balloon, right? It is helium and the latex. And we know that this balloon has a density less than the air around it because it wants to be pulled up, right? So if we take all this air and we make it helium, now the fluid inside and outside are the same, but the overall density of this object is just a little bit bigger than the helium because of the weight of that latex. So this balloon should sink. And indeed it does. Amazing.
The balloon sinks to the bottom. If the jar is now lifted off the table, what will the balloon do?
Okay, they did not describe what was about to happen very clearly, right? He's not going to go, whoo, right? Okay, and just let the balloon go free. He's going to very slowly take that jar and lift it straight up. Okay? So what I want you to do right now is turn to your neighbor and describe to them what you think the balloon is going to do as that jar is very slowly and carefully lifted up. Go. right, you think you got it?
All of it.
Who wants to go out on a limb here and say what's going to happen to the balloon?
The balloon will follow the jar.
It'll follow the jar?
Yeah.
So like, is there going to be a part of the balloon that's like sticking out of the jar?
Yes.
And part of the balloon's inside the jar? Why?
Because the weight of the balloon material. So it's still heavier than the helium, but it's still lighter than the air itself.
Right? And so this balloon is going to float, partially submerged in the air below the jar, right? And then have the helium above it. What is this exactly like?
Floating in water.
A boat. A boat sinks far enough into the water until its weight in water is displaced, everything cancels out. So part of the boat is in water, the rest of the boat's in air. Same thing, only the water is air and the air is helium. That got too confusing. Let's just watch that.
It floats at the bottom of the jar. If we tip the jar to let the helium escape, the balloon floats back to the top.
Be careful. There you go. All right. So speaking of balloon, I've got this one. Okay. And if you came in just shortly after class began, if you were here earlier, you saw me trying to get this thing. Okay, so Mason helped me out. It was floating, right? It was. You guys have changed the density of the air in this room unfairly. Had it all calibrated. You guys really changed the density of the air in this room. Okay, there we go, right? It's got a little bit of an upward tack to it, right? And I can sit here kind of all day long and try to get this thing to just float perfectly in one spot. And I've almost got it right there, right? Okay. So what can you tell me about, let's just assume it is staying. It gets higher in the room and then it starts because the air is warmer up there. I can cover that. Okay. So what can you tell me about like the net force on this balloon? Assuming it did stay in one spot.
Cancels out.
Everything cancels out, right? The net force has to be zero. So when we consider what's going on with this balloon, right, we have to make sure we understand. Okay, so what force is acting up? Oh, the helium is an object. What's the force? It's the buoyant force, right? Okay. There's a buoyant force lifting up the balloon. Okay. That comes about because the balloon has displaced, okay, some of the air. The helium inside of the balloon is less dense than that air, right? And it'll float. Okay. So what's pulling down? Weight of what?
Straight plus that.
Okay, so there is a string plus this payload down here, right? So we'll just kind of take the string and this payload. We'll just take that all together, okay? And say it's the payload, right? So yes, we have the mass of the weight of the payload. What else? Okay, gravity is the force that's pulling it down, but what are the things that are causing gravity? Yes. What are the objects that, there's more than one thing that's causing weight here. Ooh, the material of the balloon, okay? Does that latex have a weight in and of itself? Okay, so we've got the weight of the payload, we've got the weight of the latex, and there's actually one more thing. The weight of what? The helium that's inside the balloon. Okay? The helium inside this balloon does have weight. Gravity does pull down on that helium. Okay? It pulls down on the latex of the balloon, and it pulls down on the payload. All three of those forces try to pull the balloon down. The force that's pulling the balloon up is the buoyant force. Okay? The force that arises because of the displacement of the air that the balloon causes. Okay, so using this as an example, let's see how big a balloon would have to be if we wanted to bring internet, broadband internet to Fresno via balloons. Right? I'm sick and tired of paying Comcast anything. Right? Okay? And I just want to bring broadband to the masses. So we're going to get a balloon, okay? And we're going to ask the question, how much helium would it take? And how big of a balloon would you need in order to float a broadband internet antenna at ground level? We know that as it goes up, the density gets less, so we'll need even more helium. So like we're going to specify like a minimum floor, right? And we would need more after this, okay? So I went out and I looked up sort of what these features are of a broadband communications antenna. These are kind of antennas you might see on a cell phone tower, okay? One of those big fancy cell phone towers that's got all the antennas on it, that kind of stuff, right? And I found that the average mass was 4,000 kilograms, okay? So that's 4 metric tons of payload. So that's a lot. Okay? Your car weighs a little bit less than that. So we're basically lifting a car. And so I went out and I looked up some websites about, like, there are companies that build balloons and they specify, like, this balloon can do this kind of payload and so on and so forth. So I looked at specifications and discovered that the balloon that would be required to lift a payload like that, the material all by itself, just the envelope of the balloon is 600 kilograms. Okay? That's about 1,200 pounds. It's like half a ton of just balloon material. And when I'm talking about balloon material, I'm talking about like polyethylene, right? Like trash bag material. Okay, this is what these balloons are made out of, right? Really thin versions of this. And it's nice because you really kind of have to work at it to poke a hole, but it's nice and strong and stretchy, okay? So that's a bit, 600 kilograms of this. How big is this balloon going to be? Big balloon. There's going to be a lot of sad clowns in Fresno. Because we're going to use up all the helium. All right, let's do this. Free body diagram. We have our balloon, okay? And we know that the buoyant force is pulling up. And we already talked about how there's the mass of like the antenna times G. So there's the weight of the antenna. And we'll assume in that antenna, it's the string and everything that's there. Then we have the mass of the balloon itself, the material, right, that the balloon is made out of. And then, very easy to forget, the mass of the helium, the gas that's inside of the balloon. Unlike this balloon, where that seems like a very small thing, right? In this balloon, there's going to be a lot of helium. We gotta support its weight too. So, knowing that we want to just barely float this balloon and cause it to hover, so the net force on it is 0, we know that we have the buoyant force acting up, the weight of the antenna, the weight of the balloon, and the weight of the helium all acting downwards. Okay, what do we know here and what do we not know? Do we know what the buoyant force is? We don't have a number, right? Do we know the mass of the antenna? Yeah, do we know the mass of the balloon? Yeah, okay, so those two middle terms I'm just going to kind of stop thinking about. They're just known things, numbers. I can put them in later, right? Do we know the mass of the helium? No, but that's kind of what we want to find, right? Okay, we're after that. So that's a good thing. We also know what planet we're on. But we also know that the buoyant force is going to be the result of pushing what fluid out of the way? Air. How easy is it to mess that up and like put the fluid that's inside the balloon? It's easy to do, right? Make sure you're thinking about the fluid that gets displaced, the fluid that gets pushed out of the way. In this case, the density of air and the volume of air that is displaced. Now, since the balloon is completely surrounded by air, what do we know about the volume of air and volume of the balloon? They're equal. So we're going to be working under the assumption that those two things are the same. All right, so let's put that in. So we got density of air times G times, and I'm just going to do volume of balloon now because volume balloon, volume of air, same thing. Minus the mass of the helium times G minus these things that are now known. Okay. Ooh! What appears in every term? Waha! What does that mean? We just figured it out for Venus and Mars and anything else, right? Okay, as long as we nail the density of the fluid that gets displaced. In the case of Venus, the air would be mostly carbon dioxide instead of nitrogen. But I love physics. It solves everything. All right. So, well, it doesn't solve taxes. That's a different story. Okay. Can we just solve this for the mass of the helium now? Well, mathematically we can, but there's still another unknown. The volume of the balloon. We don't know how big the balloon is, right? So I've got one equation with two unknowns. Mass of helium isn't known and volume of balloon is not known. I need another idea, another equation, something. Huh? What? What's that?
Do we have an equation for volume?
We do, but we actually have a connection between the mass of the helium that's required and the volume of the balloon that's required. Density, right, is a mass divided by a volume. So the mass of the helium that's needed would be the density of helium times the volume of helium. But how much volume of helium are we going to have? The volume of the balloon. Right? Kind of by definition, whenever the mass of helium is in here, right, it's the density of helium times the volume of the structure. All right. So we can go ahead and substitute in now. So we got density of air, volume of balloon, okay, which is something that we want, right? Find the volume of helium necessary. That's the volume of the balloon, right? Minus mass of helium, which is density of helium times volume of the balloon, minus the mass of the antenna minus the mass of the balloon. All right. So now the only unknown that I have is the volume of the balloon. So I move my two numbers over, they're both negative, they become positive. And then I factor out the volume of the balloon. I'm just doing algebra now, minus mass of helium, right? And then I solve for volume of balloon by dividing. So the balloon, all divided by density of air minus the density of helium. I throw some stuff in. Antenna, 4,000 kilograms. The balloon, 600 kilograms. Don't need to put kilograms in there, just working in standard units. All right. Density of air, 1.2 kilograms per cubic meter minus 0.179 for the density of helium gets me a balloon that is equal to 4.14 times 10 to the 3 cubic meters, or approximately 4,100 cubic meters. How big is 4,100 cubic meters? How big is this room? This front wall is a little bit more, but let's round, it's 10 meters, okay? And this side wall is about 10 meters. And the ceiling is about 3 meters up. Call it 4, just to make it easy, right? So 10 times 10 times 4 is what? 400, right? This balloon is 10 times bigger than this room. That's the size of this building. About 3/4 the size of this building, because we have like 15 rooms in this building, right? Okay. It's a big balloon, right? That's a big balloon, and the only thing I'm making up in this problem, okay, is the fact that this is my idea. This is not my idea. This is from a BBC News article. Broadband net goes stratospheric. The latest broadband delivery system has seen researchers looking to the skies to provide super fast internet access via airships. Airships in the stratosphere beaming back broadband capable of fast speeds seem like fantasy. Tests in Sweden is suggested to become a reality within 3 to 5 years. Successful trial of the technology has been conducted by researchers. Trials using a 12,000 cubic meter balloon. Flying at an altitude of 24 kilometers for 9 hours proved to successfully operate the data link. I want to know why this isn't a thing.
Because the Hindenburg.
No, this is helium. This isn't hydrogen. We're not filling it with rocket fuel.
Laser pointers.
Laser pointers. This article was written in October of 2005. What happened? And why are we not living in a steampunk era where balloons are floating above our cities sending us internet? The answer has everything to do with 3G, which you guys know as the really slow speed on your phone, right? Because now it's LTE. But around this time, the speed of cellular networks was rapidly increasing, and they were going from 3G to 4G, which is called LTE. And now we got 5G ultra wide and all these fancy terms. It's faster speeds. Okay, I just simplified like 10 years of research and then set this right there. That's kind of unfair. But the point is, right, that it was economically more feasible to build a tower on the ground that's only 100 feet high than it is to float a balloon, right, above a city that has a 5 metric ton mass hanging over the city, right, waiting for it to come down. Facebook, Google, a lot of big, Amazon were trying to do the same thing with like solar powered planes that could stay up indefinitely, way up high to bring internet to places in India and China and Southeast Asia. But what happened there is that they just built out the cellular infrastructure, and balloons were no longer necessary. To see what these balloons look like, this is the balloon that Felix Baumgartner used to ride to the edge of the atmosphere and then be the first person ever to, in free fall, break the speed of sound while not being in an aircraft. I'm not sure if you can define his spacesuit, okay, as being an aircraft, right? Because it didn't provide any lift, right? But yes, he became the first human being unaided, well, aided, but without an airplane or a rocket to break the speed of sound. Okay? He did so riding a balloon that was about as tall as the Statue of Liberty, right? He rode that balloon for about 6 hours from ground level up to about 125,000 feet-ish, and then jumped out and was in free fall for 6 minutes. I think. Yeah, okay. It's a fun video to watch, okay? Especially because they weren't sure if he was going to black out. He got into 2 flat spins on the way down. Flat spin is sort of an uncontrolled rotation, and and there's no atmosphere to kind of like push against. Is sort of the problem, right? And so he had to go through training in order to like try to like contract muscles in different parts of his body to keep the blood flowing to his head, right? or the other way around. The blood was rushing to his head. So it was a red out, not a blackout. But anyway, it was quite the feat. As you can see that balloon there going up. You see how that balloon looks slightly deflated, right? Slightly collapsed at the bottom. These things take off looking like an uninflated balloon. They look like a garbage bag that's just been left on the ground. Like they're hardly big at all, right? And they're very floppy. And the reason they do that is because as it rises to the atmosphere, it expands, right? And so by the time it gets to its target altitude, it's fully expanded, right? Fully inflated, without having drawn any other gas. It's just density changes and all that kind of stuff, right? But I still contend, right, that balloons are some of the funnest things ever. And man, the density in this room is changing a lot. Gone through 4 inches of tape already. The time it's taken for you guys to heat up the room. All right. Oh, we're doing good. We're doing good. This is fantastic. Bernoulli's equation. All right. Everything we've done up till now has involved something called fluid statics. In other words, all of our fluids weren't moving places, right? The air around this balloon was considered to be static. The helium inside the balloon was considered to be static, not moving, right? So now we're going to do fluid dynamics. And as soon as I say the word dynamics, you know what happens. Everything gets harder, right? Right? Okay. So I'm going to do something that's a bit out of character. I'm going to flip this one on its head. You know me. I like to give you concept and idea first, give you this foundation and visualization with this to work on, and then we add the mathematical models on top of that and figure out what's going on. We're going to reverse that to this time, okay? We're going to do the math first, okay? And then we're going to talk about its implications. Bernoulli's equation is the master equation for fluid dynamics. You'll see here. Okay, so let me write it out. This is a bit of a Mr. Balogh style. You'll see this in books, but there's another way to write it that I don't like as much, and I'll explain that here in a second. Okay, whoops. Bernoulli's equation: pressure plus 1/2 rho v squared plus rho g h. Okay, so rho gh you've seen before. Remember when we were playing with pressure last time? And you dive down into the pool and the pressure only depends on the height, right? Okay. The P out in front is kind of like your ambient pressure. What is that term sitting in the middle? Ooh, it's got velocity in it, right? And what's more, it looks a little bit like something that we've used a lot. Okay, let me finish it. This is equal to. Now, this is where I deviate just a little bit from some of the way textbooks do.
Are those both rows or is one pressure?
Pressure P on the very front, and the other two are rows. Yeah, densities. Okay. So in a lot of textbooks, they'll write is equal to a constant. Okay. And there isn't a number for this constant. It's just equal to a constant that is constant throughout a fluid that is moving, and that doesn't help anybody. Okay. So which is why I don't like using it. It's true, but it doesn't help. What it's really equal to is exactly the same thing, but at a different place in that fluid. So Bernoulli's equation for fluid dynamics, for the motion of a fluid, inherently has built into it an idea that we want to look at one spot in a moving fluid, say in a pipe, okay? And then look at a different spot in that pipe. Maybe it's higher, maybe it's lower, maybe the pipe's changed its radius. And compare what's going on between those 2 points. What does this feel like? Conservation of energy, doesn't it? 2 points, an initial and a final. They have to be the same, beginning and the end. There's no work other term here. There just isn't. Okay, right, okay. There is in reality, but we're ignoring all of that, okay? Our fluids are always going to be nice fluids. They're going to be laminar flow, meaning steady flow, no turbulence, no friction between the pipe and the fluid that's traveling through it, right? Ideal physics stuff. But this is conservation. Like it's like, oh, what does 1/2 rho v squared just feel like? It feels like kinetic energy, right? And what does rho GH feel like? It feels like potential energy, doesn't it? It's not! What are the units of rho GH? Put together, what are its units? It's a pressure. What are the units of P? PSI, pressure, pascals, whatever, right? It's a unit. P is in pressure units, right? Rho GH is in pressure units. And 1/2 rho V squared has to be in pressure units in order to be able to add all those things together. So this is like maybe more strictly a conservation of pressure equation, right? Okay. But that doesn't change the fact that we can borrow all of that knowledge and learning and blood, sweat, and tears that we went through for conservation of energy and overlay that approach onto this equation. And that's exactly what we're going to do. The generic setup of this, you want to kind of imagine maybe a thicker pipe, right? That maybe transitions into a thinner pipe that maybe goes up to a different height. So like when you call the height of a pipe, you're really talking about sort of its midline and where it's located. And then we would have another height up here. We might take a look at the area here versus the cross-sectional area up there. This very bad drawing of what looks like a sad duck is a schematic of kind of what your house looks like from a fluid dynamics point of view. You have a main line that feeds your house, and then that branches off into other pipes that are smaller and then also go up higher, right? Because the main line's in the floor, and then you have things that come up to the sinks maybe, or if you have a second story, it has to go up to the second story. So you're changing the height of the fluid levels. You're changing how fast the fluids are moving in those pipes. You're changing the diameter or radius of those pipes as they go. It's a lot of stuff that can be happening within a system that involves fluid dynamics or moving fluid from one point to another. There's another equation that's going to come in very handy. That equation in that box right there is called the equation of continuity. It's got very interesting units. What happens if you take an area and multiply by a velocity? What do you get? What are the units of area? So meter squared times a meter gets you a meters cubed per second. That's a volume per time, isn't it? The equation of continuity is a flow rate equation. It's a volume per time, a volume rate equation. And what it says is that if you have, let's say, 10 gallons of water per minute flowing into one end of a pipe, what has to be true about the amount of water that comes out the other end of the pipe? It has to be the same. You can't send water into a pipe and have it magically disappear, right? But more interestingly, what happens if your area decreases? What if you go from a big pipe to a small pipe? According to the equation of continuity, right, if area 2, right, is smaller than area 1. In other words, we've got a pipe that starts big and maybe constricts, right? So here's area 1, here's area 2. If I solve for V2, well, that's going to be area 1 over area 2 times the velocity in 1. What kind of number is this ratio if area 1 is bigger than area 2? It's a big number, right? It's bigger than 1, which means that velocity 2 is going to be what? It means that the speed of that fluid is going to increase as it moves into that narrower pipe. In order to keep the flow rate the same, fluids have to speed up if they're forced through a smaller pipe, smaller opening. And the opposite, what happens if you go from small to big? The fluid will slow down.
Is that like on a river?
On a what?
Like a river?
Yes, rivers do exactly this, right? As a river narrows, the speed of the river will pick up, right? Otherwise, it just floods. Kind of what's happening a little bit right now.
Does that mean that the pressure increases too?
So we'll get to that. We're getting it. Okay. Hold your horses. Yes.
Do they use this principle to make like the super high pressure like water cutters?
Yes. Yeah. Okay. So there's something you need to understand about fluid dynamics. It is insanely hard. Like, some of the world's first supercomputers were invented to solve fluid dynamics problems. They're that hard, okay? Because there's a lot of stuff that goes on in a quote-unquote real world scenario. And I'm guessing for a water jet cutter that's got beads of silica and sand and other things in there, right? That are all moving, that is not laminar flow, right? That's very turbulent flow, right? And so I'm going to kind of get into that, okay? Towards the tail end here. We want to keep it simple right now, because this is something that you've experienced if you've ever used a garden hose, right? You're sitting there, you're watering whatever, okay, and a target of opportunity comes by. It could be brother, sister, cousin, cat, dog, whatever, squirrel, okay? And you just can't help yourself. You're a human being. What are you going to do? Attack. Right? So what do you do to get the water to go further? You put your thumb over the end. What have you just done? Change the cross-sectional area of the pipe. And so what does the water do? Moves faster. In other words, goes further to be able to hit that thing, right? So you've done the equation of continuity, just sort of, right? All right. So these two equations are going to be our only two in the toolbox for fluid dynamics. Let's do an example of using them, of sort of setting up this conservation of energy type situation. And what I want to do is I want to do the example of a siphon. And I've actually brought a siphon with me. Let me get the pieces that are not friendly to siphons out of the way. All right. What's a siphon?
Use it for gas.
Use it for what? To get gas? You're not going to talk here. Yeah, so I once had to drain gas from my in-laws' fuel tank with their permission. Okay, we had to repair the fuel tank. And so, yes, I did get gasoline in my mouth at a young age. So a siphon can be used to transport a fluid from one place to another. Now, before I teach you how to do criminal activities with cars, do note that many cars have an anti-siphon valve on them that makes it marginally more difficult to. It's actually, I shouldn't say things like this on YouTube. It's easier if you have access to the engine compartment to just pull the fuel line off the fuel pump and let the fuel pump do the job for you. But anyway, let's not talk about that. Put a hose, right, in a container of water. See the water level right there, okay? And then what do I have to do to get this thing started? I got to suck on it, right? Okay. Why do I have to suck on it?
Use that initial push.
That initial push, nothing's going on right here, right? Okay. I don't want that water in my mouth because it's Fresno City water. Uh-oh. What happened? Yeah, in order for the water to flow, what must be true? The water level, the level of this hose has to be lower than what? The water level in my tank right here. I can shut it off and start it. And what happens if I make it further down? It just flows faster, right? Okay. So this is a siphon. And as you can see, the speed at which the siphon works entirely depends on how much different the height is, right, between these two things. Anybody need to go bathroom yet? See, I hold my hose up here. What can you tell me about the level of the water in the hose compared to the water level in the tank? They're the same. All right. And then, just to show you that you don't actually have to suck on the hose in order to start a siphon. Okay? The reason you have to suck on the hose is not to provide a pressure difference. It's simply to fill the hose with water. If I take this hose, come on, get in there. Okay. And I push it in there, making sure at every point that I'm pushing it in so that water fills the hose completely. Okay, so there we go. I do have this hose completely filled with water. I'm going to hold my finger over the end so the water doesn't come out, and then I'm going to let go. Whoops, miss. I do, in fact, have a siphon, right? The pulling, the sucking just gets fluid into the system. That's all it does, right? After that, it's just a difference in height about where the end of this hose is. While we're here, as a side note, come on, start flowing. Oops, did we let air in? We let air in. The very tip of the other end of this hose got into the air. I really don't want this in my mouth because this is a kitty litter bucket. I did wash it before I started. Still, kitty litter. All right. What's happening to the radius of the water stream as the water falls? It's getting smaller. Why is it getting smaller? You can see this, I don't know, maybe you tripped out on this in the morning, right? When you don't want to do anything, you woken up and you're watching the water fall out of the, right? Okay? And it's coming, it starts off thick and it gets narrower and narrower and narrower, and then finally it breaks up into non-laminar flow. So the smoothness, that's laminar flow. So why is it getting narrower?
Because of gravity?
Okay, but what's gravity doing? It's accelerating the water, isn't it? So the water's moving faster and faster and faster. If it moves faster, what happens to the cross-sectional area? Equation of continuity. If you come up here, please be very careful. There's a wet spot on the floor up here. All right, so let's solve the siphon. We are going to solve for how fast the water flows out of the end of that tube. We want to get an equation for the speed, right, that the water flows out. And we know that that speed should be 0 if the two levels are equal, and then it should get more as it drops down, right? So I have this tank, okay, and I'm going to fill it with fluid, and I'm going to put a hose in it. For some reason I always like to draw my hoses as like hoses, not just a line. And we're going to, okay, so we've got fluid that's like squirting out down here, right? We need to pick 2 points. 2 points about which we know things in this system. One of those points will be the water squirting out at the end, right? We are looking for that speed, and so we want to make sure that we set this as one of our points. Well, let's call it point 2 because it's just down low. Okay, that's our final point. And now we have to pick a point somewhere else that we know information about the fluid and the system and everything else. Any guesses? The water in the tank? We're going to do it right at the surface of the water. The reason we're going to do it at the surface of the water is because we know the pressure right there. What's the pressure right there? It's atmospheric pressure, isn't it? Okay. We are also going to make an assumption here that the speed up here is 0. In other words, if I were trying to drain a swimming pool with a garden hose, okay, that would be a lot of water in a little tiny hose. So how fast would the surface of that water be moving? Really slow, right? So either think about a system where there's so much water, a little tiny hose, that the water's barely going down. Or, if you prefer, maybe this system is being backfilled, right? As much water is flowing out as being flowed in to keep the water level the same in the tank. Okay? So either way, we're going to simplify this analysis by saying that the surface of our water is moving very slow compared to the speed at which it's exiting down there. So effectively 0. And if it wasn't 0, if we knew that speed, it's no big deal. It's just another term that's floating around in there. All right. Where are we going to put 0 for height? And why would we want to put 0 for height? Is this conservation of energy? Yes, but no. It is, but it isn't. It's conservation of pressure. But when we set up conservation of energy problems, we always wanted to put a 0 point for height, didn't we? So where are we going to put it? At the lowest point in the problem. See, I taught you for reasons. Sometimes I know what I'm doing. We're going to set our 0 height at the lowest point in the problem. All right, and now away we go, right? Initial, final, zeros. Now that we've got it, we apply our equation. P1 plus 1/2 rho V1 squared plus rho G H1 equals P2 plus 1/2 V2 squared plus rho G H2. All right. How fast is the water going at point 1? 0. So we can go ahead and 0 that term out because V1 is 0. Does the water have height at point 1? Yeah, it's above 0, so we're going to leave that one alone. Okay. Is there speed, V2? Yeah, that's what we're trying to look for, so we want to get rid of that, right? But what's the height of the fluid at point 2? By definition, isn't it? We said that that's where 0 is. It's going to be 0. Okay. What's the pressure at point 1? You already said this. It's atmosphere, right? What is the pressure at point 2? No, point 2 is outside of that hose. So this would be the pressure that surrounds the water at point 2. Also atmospheric pressure. So what does that mean I can do with these two P's? I can cancel them out because they're both 1 atmosphere or 1.01 times 10 to the 5 pascals or 14.7 pounds per square inch. It doesn't matter what unit it is because they're the same. And so they can go away. All right, I'm solving for velocity here, so I'm going to reverse this. 1/2 rho v2 squared equals rho g h. We'll just call this height h. Okay. What cancels? The density. So it doesn't matter if it's water or honey, as long as it's laminar flow and it has 0 viscosity. So again, not honey. We're in good shape. Okay. So let's see. I multiply a 2 over, and then I take a square root. And what do we get? It's everywhere. It's following you. You can't escape. When you don't know what you're doing, what answer do you give? Square root of 2gh. What just happened? What question did we ask? How fast does something go when it falls through a height h? Does it matter if it's water or a tennis ball? There's no friction. There's no work other. The answer is the same. This is one of those moments in physics where we just sit there and we go, dang, this is good. It's one of these signposts that we have some understanding of how these systems work. In what looks to be entirely different, fluids and a tennis ball end up being the same in terms of the physics, right? We came at it with maybe different symbols and a different conceptual framework, but the question is the same. The water moves because gravity pulls on it. Gravity causes that velocity, and therefore that velocity has to be the square root. This happens a lot in physics as you go and you get further into it, and you start seeing the same relationships in a different context. It's it's a signpost for physicists that we're on the right track, that the same basic underlying principles are involved in this beautiful and marvelous complexity that is our universe, right? It's one of our sort of things, I think, that sets our science apart from so many others, is that we're after that simplicity. Simplicity, not maybe in the mathematics or the conceptual framework, but like there isn't a different framework for fluids than from tennis balls falling, right? Like that framework ends up being exactly the same framework with a bunch of different symbols. All right, so that's a siphon. And a good example of what's going on. Let's pull off this one right here. Okay. Why do buildings need to be worried about Bernoulli's equation? By definition, how fast does air move inside of a building? It really doesn't, right? I mean, there are air handlers here. You could, if you listen, can you hear the air moving? Can you hear the fans going, right? So air is moving, but what would you say the wind speed is inside here? It's 0, right? Like you can barely feel any movement of the air, right? Okay. But outside the building on a windy day, the wind speed is not 0. And so there's a difference in the speed outside a building than inside a building. So let's take a look at a building, right? And this is going to be like this is like a side view, a cross section of like a wall that has a window in it, right? So the blue is like the window glass, right? Okay. I fully understand that this is not how window frames work, but I'm just trying to make a simple diagram. So we have like the interior of the building, right? Where there's chairs and desks and people standing on desks, whatever it is they're doing inside there, right? Okay. And then you have the outside of the building where that's supposed to be a bird. I tried. Really trying. Here at the end, I'm just going to give you my everything. Okay. So we know that the speed inside the building, okay, is pretty much 0, and the speed outside the building they gave us as 11.2 meters per second, right? So, and the height here is the same, isn't it? We're not looking at the fluid, the air, at different elevations or anything like that. So when we apply Bernoulli's equation, that's supposed to be a 1 squared plus rho g h1 equals v2 plus 1/2 rho v2 squared plus rho g h2. There's only one term that can cancel out on both sides of those equations. Which term is it? What's the same? Rho gh. The heights are the same, right? h1 equals h2. And the density is air. It's the same thing. And we're on the same planet inside the building as outside the planet. Well, maybe you're not. You're allowed to believe what you want to believe. But those two equations those two terms do cancel each other out. It would be, I wouldn't be surprised if you wanted to also cancel the pressures. But if one fluid is moving faster than the other, there is a pressure difference. And that's what we're going to calculate. There's a pressure difference inside this building versus outside this building because of the motion of the air outside or surrounding the building. And this is something that designers, engineers have to take into consideration when they're designing window frames. So let's figure out what that is. It looks like side 1 is our inside. And side 2 is our outside. This is how I've labeled it here. So let's get the pressure difference, P1 minus P2. I've moved P2 over to the other side, which it picked up a minus sign, right? And so if that's all I want on that side, then I'm going to move my 1/2 rho V1 over here. So that's going to be 1/2 rho V2 squared minus 1/2 rho V1 squared. I can kind of clean this up to be 1/2 rho and then V2 squared minus V1 squared. Just, factoring things out, okay?
Did you cancel out the initial since it's 0?
What 0?
Because we said I've
Oh, we did say V1 was, I was, you're absolutely right. I should have done that initially. Okay. So just, there we go. I was doing the harder problem. So interestingly there, a pressure difference is being caused by the motion of a fluid. And I can go ahead and calculate this number, 1/2 times the density of air, which I don't remember. I wrote it down somewhere. It was like 1.2. You know what? I didn't even write down what this, oh yes I did. It's 1/2 times 1.2 times 11.2 squared. And this is equal to 81.5 pascals. So like this pressure difference inside to outside is 81.5 pascals. Now they're not asking us for the pressure difference, they're asking us for the net force on the window. How do I find force if I know pressure? What do we have to cycle back to? The very first part of chapter 14, don't we? Where pressure is equal to force divided by area. Do we know the area of the window? You betcha. So that force is going to be that pressure times area. So the delta force, right? The difference in force that the window experiences will be brought about because of the change in pressure times the area. Our delta pressure, 81.5 pascals. Our area is 4 times 1.5, right? I did not. I drew an asterisk there. I'm not sure why. I know why I did it, but it's times. Okay? And so this force, this difference in force inside to outside is 489 newtons, which is approximately like 110 pounds-ish. Okay? So 110 pounds of force simply because the air is blowing at 11 meters per second, which is approximately like, was that 25, 27 miles per hour? Okay, so a fairly gusty day. In New York City, which has a lot of high-rise buildings really close to each other, as the air moves from a weather system into that city, it's forced into the narrow streets, the narrow divisions between buildings. According to the equation of continuity, what happens to the speed? It goes up. And it's not uncommon for buildings to experience speeds in excess of hurricane speed, so 75 miles an hour and above, as the air moves through. At 75 miles an hour, you're talking about thousands of pounds of force. And windows are known to pop out of their frames when the wind is blowing too fast. This is a building, I believe, that is in Shanghai, China. Okay. As you can see, the architects got really creative when they had to solve a problem. What problem did they need to solve? Big flat building with wind blowing directly on it. That's a lot of force to push that building over. So what do? Yeah, put a hole in it. Right? Okay? Right? But make sure that you design that building so that no matter what direction the air flows around it, your windows are going to stay in place. When hurricanes come through and wind speeds are 120, 130 miles an hour, you will see in the news coverage, right, the helicopters flying around looking at all the damage. If you look really closely at high-rise buildings, those are the easiest to see because they're sticking up out of the trees, you will see, like a motel, say, right? You will see the curtains out on the patio of the hotel, out on the balconies. You'll see the chairs and the lanterns and everything out on the balcony. No human put those there. How did they get there? They were sucked out. Air inside building not moving, air outside building going 150 miles an hour. The pressure difference will be inside to out and things will get pulled out. How tall is that building? I don't know. It's tall. I don't know very much about buildings. Buildings are actually kind of boring to me. But it's got to be, I mean, there's 100 stories there at least, right, if we were to count the windows. Right? So, pretty tall. I have about 5 to 10 minutes of like demonstration to do for you that I will do on Monday. And then Monday we will dive right into reviewing and I will run that review, getting us ready, right, for the exam. And then Wednesday I'll let you come and ask your questions. What's happening tomorrow in lab? Nothing. Nothing's happening. So there's no lecture, there's no lab activity. Am I going to be here? Yes. Am I going to be paid to be here? Yes. Come and take advantage of that. It's like grass. Come and get your chapter 13 homework done. Right? But I'll understand if you have other better things to do. I can't imagine what they would be because physics is the best. Right? But tomorrow there's no actual graded thing. Come and get help, and I'll see you on Monday where we will, you have enough here to finish chapter 14, no problem. But I know you're already, concentrating on chapter 13. So I'll see you then, and I hope to see you tomorrow.